Now, this model YIT equals to beta 1 XIT plus AI. This model, in this model we assume that there is unobserved effect and which is individual specific. So, that means individuals are different. So, this is called one way error component model. One-way error component model. Suppose we want to accommodate a fact that it is not only the individuals are heterogeneous, but the years are also heterogeneous. For example, you are estimating the model in a specific context where the error years are also very different. For example, some major macroeconomic policies might have taken place in that place. Let us say that I am estimating farm performance in a period after demonetization. So, obviously 2016 and 2017, 18, 19 they will be quite different, or 2010, 11, 12, 13 and 14 would be quite different from 16, 17, 18, 19. So, in that context, when you feel that there might be some kind of year specific or time heterogeneity also in the situation, then it is better to include one time specific factor also in the model and make the model two-way error component model. So, what would be the two-way error component model? YIT equals to beta 1 XIT plus AI plus let us say mu t plus UIT. So, this is called individual specific unobserved effect, this is called time specific unobserved effect. So, this is called time fixed effect. Okay. This is called individual fixed effect. Right. So, how will you estimate that type of model? To estimate a two-way error component model, you have to keep in mind this is called two-way error component model. So, again the application of LSDB only will help us estimating two-way error component model. So, you have to use this command reg then after that I dot er. So, that means I am basically adding another set of dummies, one intercept for the year as well, different years. Okay. So, we have 3 years data 17, 18, 19, 17 has been 87, 88, 89, 87 is actually used as the base year. Okay. So, this model is called two-way error component model, two-way error component model. Okay. Two-way error component model. Now, once we estimate either one-way or two-way error component model, the assumption what we make that there is individual specific heterogeneity, individuals are different. So, AI factor or mu t factor what we are including in our model, they are jointly significant, that is the assumption. So, if the individual there is no significant unobserved heterogeneity across individual, then instead of applying this fixed effect model either one way or two way, it is better to apply pooled OLS, isn't it? Please try to understand. We have combined a cross section and time series, then there are two options, either to use pooled OLS or fixed effect. So, there are two options basically if we think of. When you have combined data on cross section and time series, there are basically two options. Either we use pooled data or we use, sorry, not pooled data, I will say pooled OLS, or we used fixed effect model, right? Fixed effect or LSDV, the older version. Now, when to use FE or LSDV? When AI is significant. When AI is insignificant, right? That means, how do you check whether AI is significant or not? That means we need to apply F test to check whether A1 equals to A2 equals to dot 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 AN minus 1 equals to 0 or not. Or if it is a two-way error component model, then T1 equals to T2 equals to T n minus 1 equals to 0 or not. Okay. So, we need to check whether there is a presence of significant individual specific heterogeneity or year specific heterogeneity. If we do not check this, then it is not reasonable to apply fixed effect transformation, because I have told you repeatedly that OLS model is the most perfect and powerful model in econometrics. Unless it is required, we should never deviate from the OLS model. If there is no significant AI factored in the model, then we should actually use a pooled OLS model. We combine the data and then simply run a pooled OLS model on that, right. So, when you estimate the model, fixed effect model, if you go back, our fixed effect estimate, this is our fixed effect estimate, right. Now, Stata is reporting that F statistic also to check whether there is a presence of significant AI. Look at this, this is the F test, okay. What is the F test? This is the F test where it is showing F test that all UIs are 0, that is what we are testing. So, this is 53 and 106 and 24.59. So, how this F statistic is calculated? Basically, if you recall from our basic econometrics, Stata is actually estimating two versions of this model. One is called restricted, another one is called unrestricted. So, unrestricted means you have no restriction on AI. So, you estimate a model using the one intercept for one individual, and the restricted model is basically you put the restriction A1 equals to A2 equals to dot 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 AN minus 1 is 0. Then you calculate this F statistic based on the two R square. So, R square restricted minus R square unrestricted, that model, that formula, I am not again going back to the formula. The idea is this. So, we need to check actually the validity of the restriction. Okay. The restriction is A1 equals to A2 dot 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 AN minus 1 equals to 0, that is the restriction. We will first estimate the unrestricted one, then we will estimate the restricted one. we will calculate the R square, we will compute the F statistic, and this is the F statistics data is showing you. The value is 24.59. 24.59 and corresponding F value is F equals to 0.00000. So, which is quite significant. So, that means in this case, F statistic equals to 24.59 and P value is actually 0.0000. So, that means this is significant AI, and that is why the situation calls for fixed effect model to be estimated, not pooled OLS. So, Stata is showing that also using your data, right. So, that means from the output we have now learned many things. We have learned within between overall R square, we have learned how to estimate this model, we have learned what is the interpretation of this constant term, which is basically the average heterogeneity in the sample. We have also learned the significance of this F statistic, which is basically testing the presence of significant amount of unobserved heterogeneity. There are still sigma u, sigma e and rho which we have not yet explained, which we will discuss in our next class. Before we wind up, that means now we have learned two ways, to remove. So, that means if our model is YIT equals to beta 1 XIT plus AI plus UIT, there are two alternative ways. There are two alternative ways to remove AI from the model. And based on which particular way we adopt, we will get, if you recall, one is called first difference, and another one is called fixed effect transformation. Now, the question is which particular model to take, first difference or the fixed effect. Now, there are several cases. Case 1, when t equals to just 2, that means we have only 2 periods data, both Fe and this is both FD, first difference, this is called FD, and Fe works with equal efficiency. So, you can use either first difference or fixed effect when your time period is only 2. Case 2, when t is very large, compared to n, then FD is better. Why FD is better? Because when t is large, as I already mentioned, the assumption that AI is basically fixed or constant over a period of time, that assumption is very difficult to maintain. So, FD is better than FE. Case 3, when UIT are uncorrelated UIT are uncorrelated and covariance between XIT and UIT not equals to 0. So, that means we assume that this is AI. Okay. When UITs are uncorrelated and this XIT, the explanatory variable is correlated with the unobserved heterogeneity, then FE is better. FE is better. So, that means for applying fixed effect model, we need two things. First of all, we assume that this unobserved effect is actually correlated with the XIT, and the error term, the idiosyncratic error UIT, they are also uncorrelated with each other. But what happens when these UITs are actually, when UITs are actually correlated with each other, that means presence of autocorrelation. Presence of autocorrelation, then FD is better. First difference. Why? Because if you recall from our basic econometrics, that one of the solution by which you can actually reduce the severity of autocorrelation is first difference. Okay? So, the moment we take first difference, the severity of autocorrelation goes down. FD is better because FD, first difference, reduces the severity of autocorrelation. So, in general, we need to then understand that when time period is small, we have large or macro panel, N is very large, unobserved effect is correlated with one or more explanatory variable, UITs are actually uncorrelated. When we say that UITs are actually uncorrelated, that means we are basically talking about strict exogeneity. So, that means we are ensuring this is AI, or you can say that AI is also another component. So, sometimes we say that this is UIT. So, that means strict exogeneity, covariance between UIT and XIT. So, this is 0, then this is simple exogeneity. But when covariance between delta UI, okay, and delta Xi is also 0, then that is called strict exogeneity. So, for FE to be implemented, we must ensure there is strict exogeneity. So, that means in the set of explanatory variable, it should not include any lag dependent variable like YIT minus 1. So, these are the situation conditions that must be satisfied for the fixed effect model to be employed. Model should be large panel, n is quite larger than t, UITs are uncorrelated, unobserved effect is correlated with XIT, there is strict exogeneity. Otherwise, we need to estimate the model using first difference when t is large. That means, when t is large, basically we are adding mode of time series component in the panel. And if you inject mode of time series component in the model, we need to additionally check for time series properties in the panel setup, that we will discuss later. So, in that case FD works better, because that reduces at least the severity of autocorrelation when UITs are actually correlated with each other. So far then we have discussed about mainly fixed effect model, and the major emphasis, main assumption that we make is the unobserved. This is the main assumption, that XIT is actually correlated with the unobserved effect model. So, if this is the case, when your unobserved effect is actually correlated with some of your explanatory variable, that is the idealistic situation for fixed effect model to be employed, and we need to remove this AI from the model, because if you do not remove, that will lead to the endogeneity problem. But sometimes it may so happen that in your model there is unobserved heterogeneity, but that unobserved heterogeneity is actually not correlated with the explanatory variable. What do you do in that context? Do we really need to eliminate AI? There is unobserved heterogeneity. We cannot actually measure that AI that is there in the model. So, if we do not eliminate this AI will be there in this UIT, and for each and every UIT, that means UIT 1, UIT 2, UIT 3, for each period this AI component would be common. So, UIT will show obviously autocorrelation problem. So, from that logic, apparently we may think of removing this AI. But if when AI is actually not correlated with XIT, removing AI is actually not efficient, because the idea was this would be correlated with AI. That is why to solve endogeneity we remove this. So, endogeneity problem is not there. So, when endogeneity problem is not there, why do you take the fixed effect transformation? So, that means in a situation where there is a presence of significant AI, but that is uncorrelated with XIT, we are in a dilemma whether to remove AI or not to remove AI. If we remove AI, there is a problem, because it is actually not correlated and you are going for that fixed effect transformation. So, that will call for inefficiency in the mod estimates. If you do not remove AI, then what will happen? It will be there and sitting in UIT, and obviously that UITs will be correlated with other period UIT. So, it will call for autocorrelation. So, that means the solution what we talked about so far is not applicable in that context when this is actually 0. We need to discuss a different type of panel data model, which is called random effect panel data model, that we will discuss in our next class. Thank you.